I'm sorry for this delay, but I think that now everything is working. Okay, first of all, I'd like to thank the organizers to invite me to give this talk. I will talk about 20 minutes, 30 minutes in the maximum. So the idea today is to talk about the errors and the mitigation strategies in the NISQ era. I prepared this thinking that my public are composed by students, so I think that I have a brief overview about what is errors and how nowadays we develop strategies to mitigate and also to correct errors in quantum computers. Okay, so just to begin, our history began about in the end of the 17th and the beginning of the 18th with these guys just thinking in a way to simulate quantum states, quantum process in a machine. So the idea is that if at this purpose, the best idea was to develop a quantum machine that we can use to try to simulate and to, in some way, calculate some aspects of quantum processes. It begins about in the end of the 17th, at the beginning of the 18th, and then during these 40 years, 50 years, there is many aspects occurring. David Deutsch algorithm, Peter Shor algorithm, Love-Grover algorithm. And then 2001, we have the first implementation of the Shor algorithm where we factorize the number 50. So it's not a huge number, but it was our beginning. And 2012, John Preskill coined the term quantum supremacy. That is the period when the machines will, in some way, surpass classical machines. And nowadays, we are in this noise intermediate scale quantum era, the NISQ era, where processors contain about 50, 100, 150 qubits, and they are subjected to noise. Okay, this is our timeline. I will just try to point all or at least some of the errors that we can have in a quantum computer. So at this purpose, I will just ask you to imagine an experiment. So the idea here is just to begin with a single qubit in the 0 state, and then I implement a number of bit flips. So if I introduce 1 bit flip, it goes to 1, 2 bit flips, and it goes to 0 again, 1, 0, 1, 0. And here we have the implementation of X gate. So in an ideal scenario, we will have something like this if we calculate the expectation value of sigma zeta. This is our ideal scenario. But of course, that the life is not so easy, and there's many problems that can occur when you are trying to control quantum systems. Some of them comes from the environment, others comes from the control. So one of them is what we call as current error. So when we intend to implement a bit flip, we need to implement a pulse of pi over 2, but sometimes you have some extra epsilon, and if you do this, in the end, you reach something like this. So our ideal scenario already changed, because this extra epsilon, this control problem, will introduce a mistake in your control, and once you try to bit from 0 to 1, it will almost reach 1, or it pass a bit of 1, and then it will be accumulating, and then you have something like this. There's no environment, there is no noise, just a control problem. It's quite common as well. If you try to develop this experiment in a IBM quantum computer, you see something like this. But there's, of course, more than this. You can have bit flip errors. then it's subject from the environment, and then things like will be like this. So it's getting worse and worse. And there is much more than this. Sometimes you intend to prepare a state zero and measure, but in general, there is a probability when I measure prepare zero and then I try to measure, I just obtain 1 as a result. It's a common error. It's called readout assignment error. And when you do this, you see that this is our ideal situation, but then you have probabilities that there is a bit change. So here depends of the state that you prepare. You see something like this, but in the real scenario, this P will be changed, and it will depend of these probabilities to change from 0 to 1 or from 1 to 0. And it's another big problem, because you never reach, for example, 1 here and 0 here, because the range of your measurements just change because of these probabilities of measure in a wrong way. And it's quite common. It's called readout assignment error. If you have a look in this computer, this is the IBM Marrakesh. I have a zoom here. This is the error subject to a readout assignment error. And then I think in an experiment, I just want to prepare, for example, n qubits in 0, and then I will measure. No gates, no control, just prepare and measure. And then I will take this error. I took this yesterday, and then I see the answer of your measurement if we consider, for example, 200 qubits, and the idea is to measure the purity of your state. And the result something like this. So just to prepare and measure, all of them on 0, but since there is a readout assignment error, if you just prepare 200 qubits, the purity of your final result, you reach 0. So even 200 qubits with no control, with no gates, we will have a lot of problems. Of course, that is possible to mitigate this kind of error. I will explain to you how we can do this. But if no mitigation, with no error correction codes, you have something like this. And it's a big problem, because if you intend to do something practical, you need something like hundreds of thousands to millions of qubits, physical qubits. Here's an example for factoring. It's a bit old now. We can divide this per 10, but even that, in the easiest way, you need 10,000 qubits. For example, quantum dynamics. For factoring, you think something like 1,000,000 qubits. So we are just talking about 200. So we have a long way also nowadays to cross until we reach a functional quantum computer. It's a big problem. But there's more. For example, we have a crosstalk. If you have a look on this map, where each circle here is a qubit, if you have a look at least on 2 of them, it's impossible to block this talk. This is called crosstalk. There is an extra ZZ in a superconductor qubit, and it's almost impossible to block this connection. They get entanglement. Even that, there is no desired control in these qubits. So this is just some of the problems that we have. But then the point is how to protect quantum information, because it is certainly necessary. There's no way to develop a quantum computer, a functional quantum computer, without error mitigation and quantum error correction. Error mitigation is a task that we develop in the end of the computation, and then we do some kind of post-processing to try to fix your probability distribution. So it's a classical post-processing task. Quantum error correction is a way to codify quantum information using multiple physical qubits. This is the difference between error mitigation and the quantum error correction. I will just talk briefly about the error mitigation and about the quantum error correction, just to mention some strategies that there is in the literature concern these two strategies. Okay, a simple error mitigation that I can explain to you. I just come back to the readout assignment error. As I show you, there is this relation between the measurement, real measurements, and the ideal measurement. So we can see that something like this. But then you can just do the contrary, just take to revert the problem. Because it's easy that if you reach 0.9, for example, then when you implement this, you just fix your result. So it's possible to revert the problem if I know these numbers. And it's possible to determine these numbers. You do a lot of experiments, then you determine the amount of errors, and then in the end, you can, in some way, to fix your final probability or distribution. This is a kind of error mitigation. It's simple, but it works. Another kind of process that you can do is dynamical decoupling, also quite common at IBM quantum computer. The idea here is to try to implement extra fields, extra pulls in your qubit, since that in the end you reach a better control, a better result. You can block in some way the action of the environment. In this aspect, I have been working a lot since my PhD, and quite recently we developed a strategy to optimize continuous dynamical decoupling using machine learning with Reginald and his students. Then the idea is to find a way to implement a field that control the qubit around the Bloch sphere, not directly. They do not implement the gate directly. There is a extra way to do the gate, and then you can see that without protection, you have these fidelities, and with this kind of protection, we have almost 0.9999. We call this as a mitigation error because it's you will never reach 1, because it's just to mitigate errors. You cannot protect, you cannot block errors using dynamical decoupling. Here, you just use machine learning to optimize this protection. So the energy that you expend is quite small if you compare with the first brute or strategy. This is another mitigation error. In this paper, they introduce this idea. I will just explain the introductory mitigation error strategies here. So we have two different ones: the extrapolation to the zero noise limit and the probabilistic error cancellation. These are two strategies that they developed to try in some way to mitigate errors. So the idea from the extrapolation to the zero noise limit is to expand the dynamics of the state, and then you calculate the expectation value. That's what you measure in the end in a quantum computer. And so you calculate the expectation value in this expansion. So you have something like this. This is the ideal expectation value, but you have some problems here that you change the desired one to the noise one. And it's possible if you can control the amount of errors, and it's possible to control this amount of errors because you can extend your dynamics and then the noise acts 2 times, 3 times, depends how long you develop your gate. So you can, in some way, to write this as a linear combination, and you can define this number. You can control gamma and C. And if you impose these coefficients to satisfy this linear system of equation, because you need to control this amount of error that you introduce. This is a imposing of the algorithm. But then you see that you can diminish a lot the errors. This is the difference between what is expected and the noise one. So you see that when you take more and more terms of your expansion, then you can diminish a lot the errors for the polarizing, amplitude damping, the phasing, or even non-Markovian environments. It's a really nice strategy. There's some new results that shows that if you can mitigate this kind of error, then you can simulate it in a classical computer. So there's no advantage, in fact. But anyway, at least it was a good idea. And there is other strategies that you create your unitary gates, but basically in noise gates. And then you create a linear combination of noise gates to develop your desired gate. And then you can, but now you need to know exactly what's the gate present in your computer. But if you know this, then you can just create a combination of different noise gates to produce a unitary gate. The idea is like something like this. I need 10,000 shots to create to calculate the expectation value, but then I take 500 shots using a noise gate, another 1,000 shots using a different gate, and in the end, the result is equivalent to a unitary gate. This is another kind of mitigation error. So if you pay attention to the results, this is without mitigation. So is the error is, they take just, I think that 500 simulations, and then without mitigation, all of them the errors is around 0.2. But if you introduce mitigation, then you see that many results reach a small amount of errors. Okay, what about the quantum error correction? This is the usual strategy, that is the first ones. So the idea is to try in some way to codify the state in more physical qubits. So here we are using 3 qubits, physical qubits, to implement 1 logical qubit. And here's the same. Here's to protect against the phasing. Here to protect against bit flip. It was the beginning. Here's the Shor algorithm to protect against the phasing and bit flip. Then they use 9 qubits, but things are getting better and better. And nowadays we have something like this. This is a topological qubit, because now surface code, I'm sorry, this is a surface code that you use these, each one of these is a physical qubit. So, and here we have just 1 logical qubit. So you see you have 100 of qubits to codify 1 physical qubit. This one black and this yellow one are the data that you use to store your information. These blue ones are used to detect errors, and then in some way use a syndrome to correct the state. These surface codes, they can be subject to D. This is D5, 5 per 5. So it's a D5. It's D minus 1 over 2 errors. So it's possible to block here 2 errors at the same time in this kind of topological surface code. Quite recently, Google team shows that they can even increase the lifetime of a qubit by 2.42, something like 2 times more, if he compare with the physical qubits. So in some way, we are getting protection, but here is a memory. I just create a state, and I try in some way to keep this state safe. And then using something like 100 qubits in a distance 7 code, they can protect this by this amount. In a distance 5, 2.14, and then they use, I don't know exactly, but more than 50 qubits to protect this information. Quite recently, they introduced also machine learning to, in some way, to detect faster these errors and also to correct these errors that occurs in the memory of the state. Okay, I think that was fast enough, but it gave me 20 minutes, so in 20 minutes is what I can do. So I asked to GPT to create a sentence to finalize. So here's the sentence. While the journey ahead remains long, the strides we are taking are nothing short of remarkable, moving us closer to a future where quantum computer reaches its true potential. That's a good phrase. Thank you very much.